Okay, hi, Yoni Nazarathi here, and let's read something from chapter 2 of our book. The chapter title is Principles of Machine Learning, and this is from the book, The Mathematical Engineering of Deep Learning by Benoit Liquet, Sharat Moka, and Yoni Nazarathi. That's me. So you'll get a taste of the book via this introductory section, section 2.1, Key Activities of Machine Learning. So the world of machine learning intersects heavily with both the worlds of statistics and computer science. In statistics, data and randomness are key. In contrast, in computer science, algorithms and computations are the focus. Machine learning borrows from both worlds and is about the combination of data and algorithms. It's all about training mathematical models on a computer in order to classify data, predict outcomes, estimate relationships, summarize data, control complex processes, and more. We now present and characterize a few key activities of machine learning. These activities are carried out when training, calibrating, adjusting, or designing machine learning models and algorithms. Many of these activities are loosely called learning, while other activities involve prediction or decision-making. Any activity of machine learning can be described as an interaction between the following entities: data, models, algorithms, and the real world. By data, we mean both collected data, such as the XY features label pairs described in the previous chapter, or data that is generated as output of models or algorithms. By models, we mean mathematical objects stored and implemented on a computer, together with the parameters that specify these objects. By algorithms, we mean the procedures for creating models, procedures for creating output datasets, as well as procedures for using the models themselves for prediction or related tasks. Finally, by the real world, we refer to scenarios that allow generation of data, annotation of data, as well as usage of output data for decision-making and control. Machine learning activities are often dichotomized into two broad categories: supervised learning and unsupervised learning. With supervised learning, data is assumed to be available as XY pairs, where each feature vector X is labeled with a Y. In the case of unsupervised learning, one only observes data points X and tries to find relationships between the various elements, variables, or coordinates of X. To understand this terminology, consider the learning of babies or toddlers, which only involves the exploration of input sensory data without any indication of what is what. This is unsupervised learning, since toddlers are typically not told explicitly, this does this and that does that. Then later on, for example, during school, humans also engage in supervised learning, since language and text are used to present the learners with examples X and their outcome Y. A key activity in supervised learning is the usage of data to learn or train models for prediction. See figure 2.1a. This prediction is called classification, in case the labels Y are from a finite discrete set, and is called regression if the labels Y are continuous variables. There are also other cases of prediction where the labels Y are vectors, images, or similar. A related activity is obviously to use the trained models for prediction when presented with unlabeled data from the real world. This is a vertical path in figure 2.1a. Clearly, both the training of the models and the prediction of using the models execute algorithms. Sometimes a trained model is called an algorithm as well, since it may be integrated in part of a bigger system that uses it. Most of this book focuses on supervised learning, and we begin in the next section, section 2.2, by overviewing key concepts of supervised learning. With unsupervised learning, there are other activities beyond prediction, regression, and classification. See figure 2.1b. One important activity is clustering, focusing on finding groups of similar data samples. The output algorithms that perform clustering are typically not considered as models, but rather modified data sets that incorporate the clustering information. Another key unsupervised learning activity is to carry out data reduction, where high-dimensional vectors are transformed into lower-dimensional vectors that still encode some of the key relationships between variables. While unsupervised learning is not the focus of this book, several unsupervised learning algorithms are overviewed in section 2.6. Beyond the dichotomy of machine learning into supervised and unsupervised, there are also additional popular activities that aren't directly categorized as such. One popular class of activities is reinforcement learning, introduced in Chapter 10, in the context of deep learning. Here, a temporal component is key, and an agent is trained to carry out tasks in a dynamic environment. An additional class of activities is generative modeling, introduced in Chapter 9 in the context of generative adversarial network. Here, models are trained to create artificial data sets with characteristics or a distribution similar to the input data set. An additional suite of activities is transfer learning, discussed in Chapter 8 in the context of deep learning. Transfer learning is all about taking models that have been trained for one domain and adapting them to other domains with new data. Related is active learning, also briefly discussed in Chapter 8 in the context of deep learning, where the learning process is not static, but is rather informed by the performance of the model on unseen data. This is very loosely related to semi-supervised learning, also briefly discussed in Chapter 8. Here, like supervised learning, there are both feature vectors X and labels Y, yet only a subset of the feature vector have accompanying labels. The learning process tried to use all of the available data. Finally, self-supervised learning, briefly discussed in the context of deep learning natural language processing, is in Chapter 7. It creates additional models where sequences of data are used to self-predict the future or missing elements of the sequences. This is useful for language models and related tasks. Data, seen, unseen, training, and testing. Data is a central part of machine learning. In considering data, it is important to distinguish between seen data and unseen data. Seen data is the data available for learning, namely for training of models, model selection, parameter tuning, and testing of models. Unseen data is essentially unlimited, since it is all the data from the real world that is not available while learning takes place, but is rather later available when the model is used. This can be from the future, or data that was not collected or labeled with the seen data. Needless to say, for machine learning to work well, the nature of the seen data should be similar to that of the unseen data. The underlying assumption of machine learning is that the seen data used to create models is generated by underlying processes of the real world, which are similar to the processes generating unseen data. Practically, one needs to design the data collection and labeling processes so that this resemblance between the seen and unseen data is maintained. A common practice in the world of machine learning is to split the seen data into training data and testing data. These are sometimes called the training set and testing set, and an additional name for the testing set is the holdout set. The key idea with such a split is to use the training data for learning and to use the testing data for mimicking a scenario of unseen data. It's described in section ... Some popular example datasets come with such a predefined split. In other cases, it's up to the machine learning engineer to split the data randomly according to some predefined proportions. Examples follow in the chapter. Since the purpose of the train test data split is to mimic the unseen data with the test set, one should not recalibrate, adjust, or tune models on the training set while testing repeatedly on the test set. Carrying out such a repetitive use of the test set would invalidate its resemblance of unseen data. For this reason, one sometimes performs an additional split of the training data by removing a chunk out of the training data and calling it the validation set. More on this practice and other alternatives, such as k-fold cross-validation, is in Chapter 2.5. The practice of splitting data into the train set and test set is very popular in machine learning as long as a large number of samples is available. However, in some cases, there is not enough data to be able to separate a testing set, and one wishes to use all the available data for model fitting. This is sometimes the case when working with experimental data and biomedical data. In such cases, statistical inference approaches for evaluating the quality of the model fit make heavier use of the model at hand. Some approaches for comparing models are likelihood-based and include performance measures such as a Archaic Information Criterion, AIC, or the Bayesian Information Criterion, BIC. The world of model fitting in statistical context is vast, and we do not focus on such methods further in this book. Data pre-processing. Raw data often requires pre-processing before it can be used for training, prediction, or as input to other machine learning models. A full description of data pre-processing steps and practical aspects of data processing is beyond our scope. Yet one important activity that we cover is standardization of the data, which involves subtraction of the mean of each feature and division by the standard deviation. Assume the values for some feature I are x sub I superscript 1 through x sub I superscript n, where n is the number of data samples. The sample mean and sample variance of the features are respectively computed as overline x sub I is 1 on n times the sum of j1 to n of x sub I superscript j. And the sample variance is s sub I squared is 1 on n sum of j x sub I superscript j minus xi bar squared. There's a footnote, and the footnote says, in a statistical context, one often uses n minus 1 in the denominator of the sample variance instead of n. For non-small n, this distinction is insignificant. Further, the sample standard deviation is a square root of the sample variance and is denoted via S sub I. With these basic descriptive statistics of the feature available, we may standardize the data samples of each feature I1 to P to obtain standardized samples. Z sub I is x sub I minus xi bar divided by Si. Now, the standardized data for feature I, Z sub I superscript 1 through Z sub I superscript n, has a sample mean of exactly 0 and a sample standard deviation of exactly 1. In the case that data samples of the feature are distributed according to a normal distribution, then most standardized samples would lie in the range -3 to 3. Even if the data is not normally distributed, then the standardized samples lie in the vicinity of this range and are centered about 0. Such standardization is useful as it places the dynamic range of the model inputs on a uniform scale and thus improves numerical stability of algorithms. It also allows to use similar models for different data sets that may, without normalization, have completely different dynamic ranges. We discuss such standardization also in the sequel, indicating how it can help optimization performance. Learning is approximately optimization. Almost any form of learning activity involves optimization, either explicitly or implicitly. This is because learning is a process of seeking model parameters that are best for some given task. In fact, all of chapter 4 is devoted to optimization techniques in the context of machine learning and deep learning, and a few of the sections of this current chapter contain aspects of optimization as well. In some cases, optimization is carried out directly on some performance measure, which quantifies how good the model at hand performs. This is, for example, the case when one considers a mean square error criterion for regression problems, a concept we study in detail in this chapter. However, in other cases, a loss function is engineered for the problem at hand in a way that minimization of the loss function is a proxy for minimization of the actual performance measures that are of interest. This is, for example, the case when considering classification problems and aiming to get the most accurate classifier. In such a case, optimization is typically not carried out directly on the accuracy measure, but rather on a loss function, such as the mean square error or cross entropy defined in chapter 3. In any case, the design of loss functions as part of the learning procedure is central to machine learning and deep learning and appears throughout the book. Note that in some cases, machine learning algorithms, such as, for example, decision trees, do not directly specify an optimization procedure, but rather execute a predefined algorithm for fitting a model. However, even in such cases, there is typically an inherent hidden optimization problem associated with the problem. Hence, in general, we can think of learning as a process of carrying out some sort of optimization. So thank you for listening. That was the end of section 2.1, and the next section deals with supervised learning. Thank you.